In Chapter 13, we revisit the data step again. So if you recall, we in Chapter 2 had our very first introduction to the data step where we learned the input data lines command and how to enter the data. In Chapter 4, we learned to add new variables to a data set using algebraic functions, some built-in SAS functions, if-then statements, and just learned how to create new variables, or we had these new variable assignment statements that we added to our data step. In addition to the set and merge commands of that chapter. Then again in Chapter 8, we learned to bring in a data set from an external file using an older statement within SAS, but the in-file statement. And now then, we revisit the data step again, this time to look at specifically some probability functions available in SAS. This being a statistics-based course, it seemed reasonable to put a few statistics probability functions in one of these chapters. And so we recognize from our statistics background that there are some families of distributions. When we have a discrete random variable, we talk about Bernoulli, geometric, binomial, and Poisson distributions, and we'll look at a couple of discrete distributions here. We also have continuous random variables such as those that are normally distributed or uniform. There are exponential, gamma. There are many families of distributions, and so there are some available functions within SAS that allow us to compute probabilities associated with these types of variables. So what we'll look at first is the discrete random variable, or the discrete probability distribution associated with a binomial random variable. A binomial distribution, as you recall, that we have a random variable y and it has values 0 up to a value of n that we call the number of independent trials, and we look for the number of successes given here by lowercase m out of lowercase n trials. Each trial has probability of success defined by lowercase p, where p is this probability between 0 and 1. So the idea that we're always tossing coins, it seems like, in statistics courses, so that if we toss 4 coins or a single coin 4 times, how many times are we going to see it, the heads on the upturned face, and that's a binomial random variable. And so some elementary statistics books have some binomial functions built into them that compute these probabilities. So when we have a discrete random variable, the probability that the value of the random variable can take a value of a single discrete number is can be a non-zero probability, and this is the formula for that we pick up in our first statistics course. There are some selected values of p that we'll see in reference tables and selected values of n and m, but this gives us an opportunity to look at some probabilities associated with other values of p than those that say are multiples of 0.1 or 0.05, etc. So we look at the prob binomial function. So this is the SAS syntax for that, and so prob binomial, and then in parenthesis, this is order important, what you put in here for arguments, and notice they're separated by commas. P is the probability of success, n is the number of independent trials, and m is the number of successes in those n trials. So those have to be in a specific order for this prob binomial function to work. Most of the SAS probability functions compute what are referred to as cumulative probabilities. That is, probability that our random variable is less than or equal to this value m. So the idea of some people say a left side probability. So it's a probability of m or fewer. And that's not just for binomial, but for all of these different functions that we are going to look at in this chapter. So we would take that formula that we had above that we learned in our basic class, and we add up the values from 0 up to m in the formula for y. So we can, if we have a value of m here and the cumulative probability, then we'd have m plus 1 probabilities we're adding up, because it would be from 0 up to m. That's where the m plus 1 comes from. Using the naming conventions that we saw back in Chapter 2 and the new variable assignment methods from Chapter 4, we create our new variable name equal to, and then it's this SAS function here. So we keep these in the appropriate order. So this is going to give us the cumulative probability that we refer to by this expression. In Objective 13.1, given that the probability of success on a single trial is 0.3 and that there are 8 trials, we are going to look at 4 different probability statements. Find the probability of 5 or less successes in the 8 trials. So y less than or equal to 5 is in the probability statement here. Find the probability that exactly 5 successes in 8 trials occur. That we have an interval that 4, 5, or 6, so that would include the endpoints, and the probability of more than 3 successes in 8 trials, so more than does not include 3 here. And so each of these says something a little bit different, and we are asked to use a temporary SAS data set and print the probability values. So in this data set 1, it said a temporary SAS data set, so SAS data set 1. There's no library name indicated here, no two-level SAS name, so by default it goes to the work library. We could generate these probabilities and put them in a permanent SAS data set if we so choose. We just have to be certain that the library is declared earlier in the same SAS session using one of the methods of Chapter 12. So I look at request A, B, and there were 4 parts to this question, so the new variable names I just called A, B, C, and D the same. Prob binomial 0.3 is the probability, the number of trials, the number of successes. The comments over here, again looking at Chapter 20, Section 2, if you want to learn to annotate the programs, this helps explain what it is we're doing. Of course, you don't have to annotate the programs, but this is a reminder to us that we are getting a cumulative probability here. If we want exactly 5, then we have to take the probability of 5 or less and subtract the probability of 4 or less. To get the probability of 4, 5, or 6, we compute the cumulative probability for 6, and we subtract the cumulative probability for 3, so that would isolate 4, 5, and 6 values for y that we need. If we have something that's greater than, we remember what complementary events are, and so that greater than 3 would be the same as greater than or equal to 4, and the opposite of that is less than or equal to 3, and so that complementary probability I subtract from 1. So that's how this probability statement comes about. So now then I can highlight this data step and this run statement. Alright, so we end up with our objective listed over here, and we end up with these values given here for the values of the probabilities. I didn't put any options on proc print, so I could have suppressed this, and I just kept very generically A, B, C, and D to correspond to parts of this Objective 13.1. We could use labels to expand the values of what those 4 variables mean. That would be fine. But notice here in this data set, notice we don't have a set command, we don't have merge, we don't have data input data lines, we're not infiling a data set. There's none of the previous data set creation techniques that we've learned. This is just simply defining the data set and then using these built-in SAS functions to generate values for the variables A, B, C, and D. Now, there's 4 different variables, but only one observation, and that's confirmed when we look in the SAS log here. Work.1 has one observation and 4 variables. So this is a very different way of creating a data set than what we've seen done earlier in the text. So that's using the prob binomial function. Okay, what other kinds of probabilities can we compute? The Poisson distribution is also a discrete probability distribution where the values of y are the discrete values 0, 1, 2, 3. There's no upper limit, but they are these discrete integer values for the value of the random variable y. The Poisson distribution is defined, these individual probabilities are defined in this way, where the parameter m given here is the mean of the distribution, and the syntax then for the Poisson function in a SAS data step is Poisson specify the mean and then the value of the random variable in here. So notice we have the mean to the nth power divided by n factorial. SAS using this Poisson function is computing again a cumulative probability as we show here, so that if we're going to look at values from 0 to n, it's computing n plus 1 terms. The probability that y is equal to 0 up to and 0, 1 to up to the value of n. New variable assignment, again define the new variable using the SAS naming conventions from chapter 2. So it's new variable equals and then Poisson m comma n, where n is the number of the variable y. So in objective 13.2, given that the mean of a Poisson random variable is 5.2, find the probability of 7 or less, probability of exactly 7, and the probability of at least 1. And so that we can, it says to use a temporary SAS data set to do this and to print the probability values. So in my usual careful imagination here, I have data set 2 for objective 13.2, and so that we're looking at parts A, B, and C, and so I just labeled them A2, B2, C2. This is a completely different data set than data set 1. I just put the A2 and B2 and C2 to distinguish things in our minds differently from the previous data set, but these will not be in the same data set as the binomial from the first objective. If I had named it data 1, it would overwrite the data set 1. Notice then I have here the value of the mean and then the value of y, and I've used the single line comments off to the right here again to say that's what this statement does. So get in the habit of annotating your programs. You'll really appreciate it whenever you start looking back at the work you've done. So, and then we can use proc print, and I've got a typo here. So this should be the Poisson probability distribution. And I can highlight just this part and submit it. Again, one observation and 3 variables. There's no input statement, there's no set command, there's no in-file statement. So we just have these 3 variables, one observation. And so I'm just letting things accumulate over here, and we'll look at the results. So I've got both of these. So again, good reason for using titles that annotate our output as well, and so that we have these probabilities here, and we know probabilities cannot exceed 1, and so the sum of all these probabilities here then are just under 1. And what is it we were computing here again? Probability that y is greater than or equal to 1, so the probability of 0 is the only probability kind of left out of that summation. Alright, now again, some reference books or some textbooks may have selected Poisson probabilities computed for selected values of m, or the mean, but probably not 5.2. We'll revisit some of this distributions again in chapter 14, I believe, whenever we start, chapter 15, whenever we start looking at do loops within a data set. So then we want to move on to look at continuous probability distribution. Now, most commonly we think of the normal distribution, but again, more generally, for a continuous distribution, we're looking at values of the random variable that all values within an interval can occur. And so whenever we look at discrete, we don't have all values within an interval that can occur. And so that whenever we look at the normal distribution, then in your book on page 229, you see that we have this normal curve here. And the way we figure out the probabilities associated with the normal curve are the areas under the curve. So the area under this entire normal distribution is 1. And so if we wanted to find area A, we'd have to find the probability of being between -2 and -1 for a standard normal variable z. And then between 2 and 3, that would describe, greater than 2 describes area B. So standard normal distribution has a mean of 0 and a variance of 1. And that's what the probability function associated with the normal distribution that we'll look at computes the probabilities for is the standard normal. The syntax for getting normal probabilities is a prob-norm function, and you specify x, where x is the value of the variable. So as we see in what's left, the bottom part of this figure for the standard normal, typically we're looking at things in between -4 and +4 for a standard normal distribution. Now for other distributions, of course, the range of values is broader, but we'll get to those shortly. So here I have the new variable equals prob norm x that goes into our data step. Again, follow the SAS naming conventions from chapter 2. New variable equal to this. So we will look at computing then some standard normal probabilities. That is standard normal probabilities such as A and B here. We'll also look at kind of the opposite or the reverse of computing the probabilities, and that's a little different. That is, if I know the area say to the left of a particular value is 0.9, well, we equate that with 90th percentile. If I know that the right hand area is equal to 0.75, it's going to be a value over here if the probability is greater than 1. So if that's kind of looking at things in the reverse manner. If I know the probability under the normal curve, what is this critical value of z that determines that probability? We'll also look at that. That uses a different function than prob norm. We need a function that is the inverse of that. So the inverse of the prob norm function is the probit function. And so that here you specify the probability, and this value of p is that left side probability or cumulative probability. And so if you want to find the value of the random variable that determines that left side area or cumulative probability of p, use the probit function, and it's going to again be new variable equals probit p. So we look at our objective 13.3. Given a standard normal distribution, compute the following. The areas indicated by A and B in the figure. Compute the standard normal random variable that has a cumulative or left side area of 0.9, and compute the probability of a standard normal random variable that is below 1.645. We see this whenever we look up things in our standard normal table in our first stat class. There are a couple values, we call it the Z table. There's a couple of values that stick out in our mind, and that's 1.96 and 1.645. Those are associated with 95% and 90% confidence respectively. So we already know what the answer here is going to be, we think, and so we will look at SAS and how it does that. So in data set 3, a temporary data set, the area A, it was the area under the normal curve between -2 and -1. So let me toggle back to the figure again. Okay, area A is bounded on the left by z equals -2 and on the right by -1. So what prob norm does is it says For this value -1, computes all of this area, and then for prob norm -2, it computes this area outside here. So if we compute the probability less than or equal to -1 and subtract from it the probability of z being less than or equal to -2, that will give us A. While I'm on the picture here, to get B, we need the probability of being in excess of 2. So there, since this whole area is equal to 1, we subtract the left side area over here. So prob norm will give us the left area or cumulative probability associated with z equals 2, and we subtract that probability from 1 to get the value of B. Now, moments ago when we had this on screen, we didn't have these comments here, so in the change of screens here, I've added those. So here we have the probability of being to the left of -1 in that image, and subtract the probability of being less than -2. Likewise, what's the probability of being to the left of +2, and we subtract that from 1 using complementary events. Whenever we want to find the 90th percentile, that is, what is the value of z such that the area to the left is 0.9. So it's going to find what c is. That's what we've asked for here. And prob norm, we went back to the first function, and 1.645. We use this often whenever we talked about 90% confidence intervals. If we look at the left side area here associated with positive 1.645, we can print this out. So our objective 13.3 here. All right, so the probabilities for indicated by areas A and B are given here. For C, C was what determines a 90th percentile. We have 1.28, so 10% is above. Okay, so you might be thinking a different number here. And then also D here, we have that the prob norm for 1.645 is 0.95. Well, it's not, when we talk about 95% confidence intervals, remember we divide that area under the curve into each side of the distribution. And so this says the area above 1.645 is 0.05. And that agrees with what we talk about with our confidence intervals. Similarly, this value here, if we're looking at the 90th percentile, okay, that's not going to that may not be the value that you expected. You were expecting perhaps the 1.645 instead of something a little bit smaller here. Or maybe you knew exactly where we were. Now, it's rare that our data follow a standard normal distribution, but if you have a normal distribution with a mean of 12.8 and a variance of 6. Now, some notations, be careful of your references here. The second number listed by me and for many references is variance. There are a few out there that list that second number as standard deviation, so just be attentive to that. So we can't have a prob norm function for every possible normal distribution because there are infinitely many values for the mean and infinitely many values for the variance. So there's no way to say I need a prob norm function for all of those. But what we can do, recall, is we did this transformation formula in those courses that we took that y that had a mean that was different than 0 and a variance that was different from 1, and we transformed it to a standard normal. So I can input this formula into the prob norm function using a square root function, one of those functions we mentioned back in chapter 4. And I've got some extra spaces here to kind of highlight what we're doing or getting that formula. So remember, you can use parenthesis only for grouping symbols, and so you can nest parenthesis and that's fine. Alternatively, you could enter the mu and the sigma squared as two new variables and do everything, kind of build it up one piece at a time, such as this example on the right shows. Either one of those is okay, but that's how you handle things that are different than the standard normal. Likewise, you could do a rearrangement of this so that if you know the value of z and find the value of y, that's another rearrangement, and that has a different application where you can find in the units of y, say what is the 95th percentile or what is the 75th percentile, that sort of thing. We've also seen throughout this book several applications of a t-test, sometimes referred to as student's t, and so that we look at observed significance levels for those, and so that if you wanted to find those observed significance levels, those are probabilities. Therefore, those p-values, p probability has to be between 0 and 1. And so you can use a prob t function. So previously, remember, we had prob norm. So here prob t, x is our argument here, which is our numeric random variable, and then the degrees of freedom is very application dependent. So it depends on what we were doing earlier in the book. We had n-1 degrees of freedom when we're testing a single population mean. When we were testing slopes and regression, it was n-2 in simple linear regression. So the degrees of freedom is application dependent. There's also a non-centrality parameter here, and non-centrality parameters are beyond the scope of the prerequisite knowledge for this class, but should you ever start looking at t-distributions and need to know information about non-centrality parameters, those can be incorporated here as well. Typically what we do with the the student's t-table is that we use, say, a specific value for alpha, and we determine the critical t-value. That's how we stated the rejection regions in those earlier tables in chapters 3, 6, and again in the regression chapter 11. So if we have select values for probabilities that aren't in the table, well, we can use a t-inverse function to get there. Again, we specify what that probability is, the degrees of freedom, and again, non-centrality parameter in advanced applications. But the probability here is between 0 and 1. And again, keep in mind, both prob t and t-inverse, they're talking about those probabilities being cumulative or left side probabilities again. Similarly, we can talk about a chi-square distribution. We did look at chi-square associated with a variance. And so it's when you want to find a probability, it's prob chi. What's the value of the chi-square statistic? What's the degrees of freedom for the application? Again, very application dependent. It also has a non-centrality parameter associated with it. And if we just close the parenthesis after the degrees of freedom, it assumes non-centrality parameter 0. Same thing for the t-distribution, and that's what our reference tables are in our basic courses. The opposite of prob chi is the C-inverse. Specify the cumulative probability, the degrees of freedom for the application, and close the parenthesis. Use the non-centrality parameter if you're in advanced application. So just keep in mind, these are again looking for cumulative probabilities, either as the argument or as it'll generate that as the result. So we have t-inverse, c-inverse, and now we're looking at the f distribution. So you can probably guess what's going to happen here. It's prob f, the value of the f statistic. Remember, f has two different measures for degrees of freedom: numerator degrees of freedom, denominator degrees of freedom. It also has a non-centrality parameter application, but for us, we're just going to close the parenthesis. And so this is very order important. It's always numerator degrees of freedom before denominator degrees of freedom, and then we have the value of the f statistic here. And so this is going to compute the cumulative probability or left side probability associated with an f distribution. The opposite of that, we can no doubt expect, would be f inverse, where we specify the left side area or probability and then the 2 degrees of freedom measures. Now additionally, SAS has a number of what they call PDF and CDF functions in the SAS data step associated with associated with continuous random variables as well as discrete random variables, and those go a little bit beyond what we're talking about here. So we're just kind of mimicking what we see in the reference tables and perhaps working with probabilities that we don't see in the reference tables. We'll look again at some information about these functions in Chapter 15 and where we learn to generate random samples from these different populations. So in Objective 13.4, we wanted to use the SAS functions for t, chi-square, and f to compute each of the following, and we use a temporary SAS dataset and print the results. So we want to find the value of t when our right-hand area is 0.12, and the degrees of freedom for the application is 14. Here, what's the probability? This is our value of t, and it has 20 degrees of freedom. What's a critical value? Values we'd look up in a reference table for chi-square with a right-hand area of 0.04 and 14 degrees of freedom for the application. So if the right-hand area is 0.04, the cumulative probability or left-hand area is 0.96. Find the p-value or observed significance level of a chi-square test statistic of 17.04 with 6 degrees of freedom for testing this population variance that is equal to 42. And then we have a p-value for an ANOVA F statistic. ANOVAs we covered back in Chapter 7. And find our critical value determined by alpha equals 0.03 for this situation here with 4 numerator and 16 denominator degrees of freedom. Right? We don't often test this at alpha equals 0.03. Most of us think that we have a 0.05 tattoo somewhere, but that's not true. So once again, our code for a temporary SAS dataset, dataset 4. There again, no input statement, no in file, no set commands or merge commands. They're just the declaration of these different variables, A through F, for the 6 parts of this objective. So we're looking at t inverse 0.88, that is find t whenever the area to the right is 0.12. Well, if the area to the right is 0.12, the area to the left is 0.88, and the degrees of freedom for the application is 14. Likewise, then we want to find, or opposite rather than likewise, we have the t value of 2.104. We want to find the area to the right of that. What is the probability of a t statistic larger than 2.104 with 20 degrees of freedom? So we figure out what the probability, the prob t function for 2.104 and 20 degrees of freedom is cumulative or left side area, so we subtract that from 1, and similarly for each of these remaining. Now call your attention to item D. There's a 2 multiplier here because we're looking at a 2-sided test, and so therefore we look at this right side area. Since this 17.04 is in the right side of the chi-square distribution, so we determine the area beyond 17.04, and that's what 1 minus prob chi does, and we double it because it's a 2-sided test. If we want to find the p-value associated with analysis of variance test statistics, reviewing the information from Chapter 4, that's a one-sided test for values of f that are large, so we find the area to the left of our computed ANOVA F statistic and subtract it from 1. We don't double that, it's a one-sided test. And if we wanted to find a critical value for 0.03 in the right-hand area, that means the left side probability or cumulative probability is 0.97. So once we have these, can run those and generate those probabilities as well. So this allows us to look at probabilities attached to applications that may not have a reference table with these items marked out for us, or that we can generate p-values more generally rather than just saying, well, we know that p-values between 0.025 and 0.05. Can we get it more specifically? And so these functions allow us to do that. So we've looked at discrete and continuous probability distributions in this chapter. For those of you that continue on a little bit farther in some statistics and you're looking at determining statistical power, that some of these functions can be used then to compute statistical power, and you need a knowledge of non-centrality parameters to do that. There are many more functions available in a SAS data step, but these are the ones we focus on now given our introductory background in statistical methods.